Welcome to another podcast. In this episode, we're going to be taking a look at how to take the Laplace transform of a derivative. Now, what makes this topic important is we're eventually going to want to take a Laplace transform of an entire differential equation, and in doing so, we're going to have to know how to take the Laplace transform of derivatives. So to begin with, for this particular example, I want to start by looking sort of generally at the definition. So recall that the Laplace transform of a function f of t is the integral from 0 to infinity of f of t e to the minus st dt. And if I'm wanting to look at the derivative of f instead, so I'll just look at f prime of t here, then not much would change. And if we want to figure out what's going on, we're going to have to use integration by parts here. So if I look at my parts integration, the thing that makes the most sense is letting u be e to the minus st. Du then would be minus s e to the minus st. And then our dv is what we want to pick to be the derivative. So f prime of t dt is the derivative, which makes v the integral of that, which is just the normal function f. So if we apply integration by parts here, we get u times v evaluated from 0 to infinity minus v du, but there's already a minus here from the du, so this is going to be plus, and then we have s integral from 0 to infinity of f of t e to the minus st dt. So one of the things that's very interesting here is you see this piece is already looking like the regular Laplace transform. We just have to figure out what the u times v piece out here in front is for this particular problem. Now in order to do that, we are going to have to look at the limit as t goes to infinity of f of t over e to the st. So, and the reason is because I'm going to have to evaluate this at infinity, and this is in some sense an indeterminate form. Now, when is a limit for this going to exist? Well, the limit for this will exist if and only if the function f of t that we're looking at has the property that it is slower than an exponential. And what I mean by that is, let's say that it is less than c times e to the kt for c and k constants. Then if that's true, notice that I can replace this limit with this one. So I'm going to replace f of t with c e to the kt over e to the st, and that limit is equal to 0 provided s is smaller than k. Or excuse me, greater than k in this case. If we want it to go to 0, then the power of the exponential in the bottom has to be larger than the power of the exponential in the top. So we're perfectly fine as long as the function f of t satisfies that property. Then that limit is going to equal 0. This is a special property, and if the function f of t that we're looking at satisfies that property, then we say that f of t is of exponential order. So, one of the things that we've learned right away is that if we want to take a Laplace transform of a function, then that function must be of exponential order. So all of the f of t's that we're looking at in this chapter are functions which grow slower than some exponential. Now, keep in mind that the k value here could be very, very big. So we could be talking about something that's growing incredibly fast, but examples of functions that wouldn't work would be something like f of t equals e to the t squared. I can't take the Laplace transform of that. And that's not surprising given that the integral of that function doesn't even exist. So we'd run into a lot of potential problems. So another function that would be out is a function like e to the t to the t. I know that's sort of a weird function, but those exist. And so we couldn't do that one either. So we're only looking at functions that grow slower than an appropriate exponential. And so we're looking at functions that are of exponential order. What this causes is if we assume this, so if we now assume that f of t grows slower than an exponential, then that causes this limit to be 0 as long as s is greater than k. And so what you should be seeing on a lot of these problems, if you remember things like when we looked at the exponential formula, we said that the Laplace transform of the exponential e to the at was equal to 1 over s minus a as long as s was greater than a. That formula, the s greater than a part, comes from this. It only works if e to the at is of exponential order, which it is as long as s stays bigger than that exponential we're taking the transform of. So that's why these little add-ons, or these are really domains, that's why these little domain add-ons occur for several of the Laplace transform formulas. All right, if we continue this on, plugging in 0 will give f of 0, excuse me, not just 0. I get 0 from plugging in infinity minus f at 0 from plugging in 0 plus s times, and you can see here that this integral is simply the same as the traditional integral for the Laplace transform, so this is just capital F of s to represent the transform there. Now if I carry this on out, what we have is, at least the way that we would traditionally write it, is s f of s minus f at 0. So notice that I need to know an initial value. Of the function f of t. I'm not going to be able to get by without knowing that for the problems I'm looking at. So there is the first formula that we've come up with. The Laplace transform of a derivative is s times the transform of the function minus the function's value at 0. Now suppose I wanted to find the Laplace transform of the second derivative. Well, this is one of those cases where it pays to work a little bit smarter. We're going to look at this as being the Laplace transform of f prime derivative of that. And the reason that we're going to do that is we can use the above formula. The above formula says it should be s times the Laplace transform of the function, but that's the Laplace transform of f prime in this case, minus f at 0. And then if we apply the recursion one more time, the Laplace transform of f of prime is s f of s minus, this would be f prime at 0 because that's the function here, minus f of s f of 0. And that should be okay. And then if we string it all out, what you end up with is s squared f of s minus s f of 0 minus f prime of 0. And look, as soon as we start talking about a second derivative, notice that we need not only an initial condition, not only an initial value, but an initial velocity as well, or initial rate. We need two initial points. There is a pattern here. Hopefully that you're starting to see the pattern. The pattern is that when you produce multiple derivatives, you take the Laplace transform of things that have multiple derivatives, then you produce a polynomial in terms of s that has equal size. And so in general what we have going on here is, if we were to go up to the next highest one, for example, the Laplace transform of the third derivative, the pattern that we've established here, this would be s cubed f of s minus s squared f at 0 minus s f prime at 0 minus f double prime of 0. And you can see here that that would involve 3 initial points that I would have to know at the value 0 in this case. So this is something that we're going to use repeatedly throughout the rest of this chapter. So this really needs to be something that you commit to memory and sort of understand how to take the Laplace transform of a derivative, as well as understanding what that means that your function f of t has to impose a restriction on the value of s in the transform in order to do that. All right, thank you for watching.